All right, so today we're going to be taking a look at AOI Logic Implementation. In this presentation, we're going to talk about how to design an AOI logic circuit from a sum of products or SOP logic expression, and how to design an AOI logic circuit from a product of sums or POS logic expression. Basically, what we're going to be taking a look at is we're going to be taking a look at our logic expressions and seeing how they can be turned into a schematic or a simulated circuit inside of Multisim. So when we look at taking our actual statements and implementing them into an actual circuit, we have to take each minterm in the logic expression with an AND gate and the same number of inputs as there are variables. So for example, in AB we have a 2-input gate, ABC would be 3 input, ABCD 4 input, okay? Or together the outputs of the AND gates to produce the logic expression. So if necessary, gates can be cascaded to create gates with more inputs. Realistically, we're going to take a look at first an example. So we're going to design an AOI logic circuit for the SOP logic expression that is shown below. So what we have is we have that F1 equals A naught B, C naught D, and B, C, D naught, and AB. So we need to create a circuit where these can be represented by different logic gates. So obviously our inputs are going to be A, B, C, and D. That's then going to funnel into an A and an A naught, B and B naught, C and C naught, D and D naught, since we need all of those. So using the inverters, we can create the NOT signals, and then but we just come from before the inverters to go into our logic gates. Now, we know that we have 4 inputs, so we're going to use a 4-input logic gate to create this solution right here. So coming into this logic gate, we have A naught, B, C naught, and D. Then our next portion of our expression is B, C, and D naught. So if we trace this backwards, we have B, C, and D naught. Lastly, we have a 2-gate AND gate, and that is going into A, B naught. So we have A, B naught. Once we have those 3 inputs, we put them into an OR gate, and that can then give us F1. So in this class, we actually only have access to 2-input gates, or 2-input AND gates, or 2-input OR gates, 2-input AND gates, and 3-input AND gates. So that limits our design a little bit because we have to redesign our AOI circuits with our expressions so that way they match. So looking at that same situation, we now have to chunk these into even smaller bits by using 2 input logic gates to be able to feed into our next logic gate. So this is called cascading, when we have 2 sequences that we then put together and essentially pull together to create a next logic gate and then move into here. So instead we end up with 1, 2, 3, 4, 5 AND gates and 2 OR gates versus our previous solution where we had significantly fewer gates. So looking at a product of sum logic expression in a circuit, when you implement each max term in the logic expression with an OR gate and with the same number of inputs as there are variables in the max term, example A or B equals 2 input gates ABC, 3 input gates ABCD is a 4-input gate. And then we can AND together the outputs or gates to produce the logic expression. If necessary, we can cascade the gates just like we did in the previous example. So here, because we have the parentheses in place, that is indicating that these are using OR gates, and then we have AND gates connecting them. So if we look at this final solution, we have the same setup. W, X, Y, and Z come out with W and W naught, X, X naught, Y naught, because we don't need a Y on if you take a look. And then we have Z and Z naught. This then goes into our different level of OR gates, and we finish off with an AND gate to go into F2. So limiting our design to only 2 input OR gates, 2 input AND gates, and 3 input AND gates, we have to redesign that same logic expression. So this is where we have the cascaded gates that then come in and work through this. It is much easier to do this by hand to figure out how you can cascade these gates than it is to just throw these into Multisim. Okay, so at this time, that is the conclusion of this presentation. You can now move into the 213 assignment.